Hello. Next up, we're going to work on lessons 3.4 and 3.5. We're going to do them in a couple of parts. And the first part is going to talk about measures of position. And so if you can turn into your course back to page 97. So we're going to start thinking about something called the Z-scores. So it says, suppose you get an exam back and you find out you earned a 70% on the exam. How do you feel about your exam score? Most people probably wouldn't feel great. Maybe okay if it wasn't your favorite class. So maybe okay if not your favorite class. Not good if you're needing to get really high grades, right, to get into, like, say, the nursing program. Suppose they further inform you that the mean on this exam was 60%. How do you feel now? I scored a 70, but the mean was 60%. So I probably feel a little bit better because I at least scored higher than the mean. I at least scored better than average. Suppose I further inform you that the standard deviation on this exam was 10%. Now, how do you think, now what do you think about your score? So I'm one standard deviation above the mean, right? So 60 minus 70. So we talked about this as our deviation. Remember, the x, my observation minus the mean is my deviation, which is a negative 10. And so negative means I'm under the mean, and 10, since 10 equals 10%, which is a standard deviation, I am, I'm sorry, I was above the mean, wasn't I? I scored 70 and the mean was 60. So I am one standard deviation above the mean. Okay. Suppose I instead tell you that the standard deviation on this exam was 5%. Now, what do you think about your score? So my deviation, right, my score minus the mean is still 10, but because the standard deviation is 5%, I am 2 standard deviations above the mean. So my score is now considered unusual, right? If we go by our rules that we introduced back in lesson 3.2. Okay, so this thing, by counting up how many standard deviations I am above or below the mean, is called a Z-score. And sometimes you're not even, your number of standard deviations above or below the mean is not even. It's not like a whole 1 or 2 or 3. Sometimes it's 1.7. And so to figure out that, we have a full formula, which is essentially what we just did. So there's a population Z-score when we have the population mean and standard deviation, and there's a sample Z-score when we have a sample mean and standard deviation. Notice that they're almost identical formulas, except for symbols are different. That's it. Z-scores tell us whether a particular x is equal to, below, or above the mean, based on whether it's positive or negative or 0. Z-scores tell us how far away from the mean a particular x value is, and Z-scores are unitless. Z-scores have a mean of 0 and a standard deviation of 1. Z-scores will be very important in this course from chapter 7 onward, and actually even in chapters 3 and 4. Generally, or actually chapter 3. Generally round these to 2 to 3 decimal places. Okay, so let's just jump right in here. Example 1 says, suppose the mean height of human males in the galaxy is 70.2 inches with a standard deviation of 2.99. The mean height of human females in the galaxy is 64.8 inches with a standard deviation of 2.79. Han Solo is 6'1", while Rey is 5'8". Who is absolutely taller? So absolutely means just comparing height to height, pure height to pure height. Han Solo measures taller. Okay. Explain why it's not fair to compare Han's and Ray's heights directly. And that's because males and females have different average heights. We just saw that up here in the explanation. What are some other variables we can measure that would not be fair to compare directly? Okay. I think probably our muscle strength. I know our bone density, I think, is a little bit different too. And I'm sure there's other things that I don't know about. There's any you should share them with the group. Please share them with me. Find Hans and Ray's z-scores and use them to explain who is relatively taller. So relatively means compared to their gender. Okay. So Hans' z-score is going to be his height. And remember that Han is 6'1". So he's 6 times 12, which is 72 inches, plus the extra 1 inch. So he is 73 inches tall. So 73 minus the average male is 70.2 divided by 2.99. Now, if you don't have a graphing calculator, it may be just as easy for you to have access to Desmos. So Desmos is and I think I'm sharing my second screen, but I'm going to move it over because I'm not confident I am. So Desmos is it's desmos.com. It's a really nice handy calculator. You can get an account where you can save things here. I've got all different kinds of lessons, different things I can save. So that's nice to do. And it's really easy to, you can say 73, and then I make my fraction. And then I just go up and edit minus 70.99. Oops, 70.2 is the average male. And so Han has a z-score of 0.936. And then Ray, her height was 5'8". So I can actually edit that right here in Desmos. I can say 5 times 12. 5 times 12 is 60. And then 60 plus the extra 8 inches. So she's 68 inches. So she's 68 inches. So her z-score is 68, subtracting the average for women, which is 64.8, divided by the standard deviation of 2.79. So I'm going to, and the cool thing is you will this plus button and say note. So we can say Ray. And then I can type in letters. And then here I can do another calculation, 68. I'm going to divide first to create that fraction. And then 60 minus 60. And then there is Ray's Z-score of 1.147. We'll round that to 3 decimals appropriately, 1.147. Okay, so Ray is relatively taller because she has a Z-score that is further above 0, further away from 0. So I'm going to go ahead and share that screen with you again. So Ray is, because she's further from 0. Further above 0. Because we're talking about taller. It says, Kylo Ren is a male, has a Z-score of 1.605. What is his height? Okay. So 1.605 is the Z-score, and his height is X. And we're subtracting the mean, which is 70.2, and dividing by the standard deviation. So if we multiply both sides by 2.99, this product here becomes 4.799 equals X minus 70.2. And then we can add 70.2 to both sides. And we find out that his value, because his Z-score was above the mean, we know his Z-score is bigger than 70.2. And that comes out to be 74.999. All right. So that's the gist of Z-scores. We're going to do a few more here. So on page 99, it says Poe Dameron, male, has a height Z-score of 0. What does this reveal about his height? Well, if his Z-score is 0, then we can multiply both sides by 2.99, and we still have 0, right? So his height must be exactly at the mean. So he is average height. Princess Leia is 5'1", while her twin brother Luke Skywalker is 5'6". Which one is relatively shorter? Okay, so let's do Leia here. So 5'1" is 5 times 12 is 60 plus 1 is 61 inches. Minus the 64.8 divided by 2.79. Again, if you go to decimals and type this in, you should validate that you get negative 1.362. And then notice that it was negative because she's actually shorter than the mean. She's shorter than the average this time. And Luke is 5'6", so he is 5 times 12 or 60 plus the extra 6 inches. So he's 66. 66 minus 70.2. So you can see here, calculate Luke's Z-score. We've got 66 minus 70.2 divided by 2.99. And if you put that into the calculator, you get a negative 1.405. And so they had asked who is relatively shorter. And we can see that they're both, because they both have a negative Z-score, they're both below the mean, their gender average. But Luke is a little bit more further negative, right? So if this is 0, and this is 1, and this is 2, so negative 1 and negative 2. Here is Leah, but here is Luke. So Luke is a little bit further negative than Leah, and that means he is a little bit relatively shorter. Okay, so I'm going to skip H, but I do want to make a note on the reminder here. So if a data value is beyond 2 standard deviations away from the mean of a symmetric distribution, it is considered unusual. So very large unusual values are Z's that are less than a -2. So their Z-score is going to be less than a -2. And very small unusual values are Z-scores. I'm sorry, they're right, a little bit wrong. The very large ones are greater than a +2. And the very small unusual Z values are data values that have Z-scores that are less than a -2. So kind of like the number line I drew up here. So 1, 2. So anything out here is large. And anything up here is unusually small. Okay. So we're usually just looking at the absolute value of the Z-score to see the magnitude. So let's go ahead and flip the page. So while we're talking about how far a data value is above or below the mean, sometimes we want to talk about what percentage of values are below my score, what percentage are above me. And something called a percentile is the percentage of data values. It's a value such that K% of the observations are less than or equal to PK, or K% of the data values are at or below PK. And percentiles are where the data is ordered from smallest to largest into 100, and then we break the data into 100 equal parts so that we can see what percent is below that value. So if we have 0% to 100%, let's say we have P75, then we know that 75% of the data is below. This value, whatever that value is. So we're going to look at a couple instances here to think about that. So it says your child is in the 3rd percentile for weight. Is there cause for concern? I would say yes. Because when your child is small, they want to have at least the average weight for their age, because that means that they're thriving and their body is taking on nutrients like it needs to. So yes, because only 3% of children at that age weigh less. Suppose you scored a raw score of 63% on an exam, which means you were in the 84th percentile. Was this an easy exam or a difficult one? Did you score well or poorly? Well, 63% is not a high score, but you scored higher than 84% of the class, which means it was probably a difficult one, and it looks like you scored well compared to everyone else in the class. It says, suppose you scored a raw score of 81% on an exam, which means you were in the 59th percentile. Was this an easy exam or a difficult one? Did you score well or poorly? Well, you scored an 81%, which is a good score, but it looks like 59% of people were lower than you. So a lot of other people scored higher than you. So I would say that this might have been an easier exam and you just scored poorly. It depends on how you look at it in that way. Let's look here at another example. Kind of going back to some graphs that we did back in unit 3 or unit 2. So chapter 2, it says recall from 2.3 that a relative frequency ogive is also a percentile graph where common in doctor's offices shows the cumulative percent of it for a data set. This is an ogive of the ages at inauguration of all the US presidents in as of 2020. So it says President Obama was 47 when inaugurated. Approximately what percentile was he in? Interpret the meaning of this value. So he was 47. So I'm going to go to where I believe 47 is, maybe right there. And I'm going to go over, and it looks like he's maybe around 15 percentile. I'd say the 15th percentile. Depends on where you draw the 47. It might be closer to 10. It says President Thomas Jefferson was in the 70th percentile for age when inaugurated. How old was he? Interpret the meaning of this value. So the 70th, so it's between 60 and 80, right about here. So I'm trying to go over straight over. And then straight down. And it looks like his age is about 58 years old. So this means that 70% of presidents were inaugurated at a younger age than Jefferson at 58 years old. Okay, so let's take just a little break and come back. And when you come back, we're going to be on page 102, and we're going to dive more into these percentiles.